Welcome to Understand the Math. In this Calculus 1 video, we're learning how to find the maximum and minimum values of a function. We'll start by learning about the difference between absolute and local maximum and minimums and how to identify where each occurs. We'll then learn how to find critical numbers and see how they're used to locate maxima and minima. Finally, we'll apply the closed interval method to find absolute maximum and minimum values on a given interval. Be sure to download the free guided notes to follow along and work through the examples with me. We'll begin by learning about the difference between absolute and local maximum and minimum values, and then walk through some examples. The maximum and minimum values of a function can be classified as either local or absolute. A local max or min of a function is the highest or lowest point within a small neighborhood. A small neighborhood just means points near the highest or lowest points. Down here on our graph, this point is a local minimum because it is the lowest point in the neighborhood of points around this point. This point here is a local max, and then this point here is also a local max. Now let's talk about absolute max or mins. An absolute max or min is the highest or lowest point across the entire domain. So that just means that the absolute max or min is the highest or lowest point among all the points on the graph. In our graph down here, there is no one point that is smaller than all the other points, but there is a point right here that is the highest point of all the points, and that is an absolute max. We say that a point is a local max at x is equal to c if f of c is greater than or equal to f of x for all x close to c. And then the same thing happens for a min. We have a local min at x is equal to c if f of c this time is less than f of x or equal to f of x for all x close to c. Here's one important note. A local maximum or minimum cannot occur at an endpoint because it requires points on both sides for comparison. A point is an absolute max at x is equal to c if f of c is greater than or equal to f of x. That's the same thing as the local max, but now it has to be for all x in the domain. And then something similar is true for an absolute min at x is equal to c. F of c is less than or equal to f of x for all x in the domain. Unlike local max and mins, an absolute max or min may occur at an endpoint. Let's now walk through an example. We are going to state the local and absolute maximum and minimum values of the function and where they occur. Let's start by looking at the points on our left. So we'll start with x is equal to 0, and then we'll go to the right. When x is equal to 0, our function is this value right here. Since this is an endpoint, this point cannot be a local max or min. It could be an absolute max or min, but if you look at all the other points on the graph, you can see that there are points higher than this point, so it is not an absolute max. So we just say that that point is neither an absolute or a local max or min. Let's now look when x is equal to 1. At x is equal to 1, we have a local min. Our function at x is equal to 1 is less than or equal to the points around it. Let's now look when x is equal to 2. This one's a little bit tricky. In a neighborhood around x is equal to 2, notice that our function value is equal to the points to the right and to the left. That means that at x is equal to 2, we have a local min and a local max. Let's now look at x is equal to 3. This one is just like x is equal to 1, and we are going to have a local min. Now let's look when x is equal to 4. That is going to be a local max, but it's not going to be an absolute max because there are points to the right bigger than that point. So let's just say x is equal to 4. We have a local max. Now let's look when x is equal to 5. That point is neither a local or an absolute max or min, so we won't write anything down for that point. We can say the same thing when x is 6. That is not a max or a min. But if we go a little bit further to where x is 6.5, we have a local min. So let's write down here x is 6.5. We have a local min. When x is 8, we don't have a local or an absolute max or min. But when x is equal to 9, we have a local max, and then that point is the highest point in our graph, so we also have what's called an absolute max. So we'll write down at x is equal to 9, we have a local and absolute max. Hang with me, we have 2 more points to go. When x is 10, we don't have a max or a min. And then now let's look at what happens when x is 11. Because that point is an endpoint, we cannot have a local min, but we can have an absolute min. And if you look at all the values of our function, when x is 11, that is the smallest value. So we're going to say that at x is equal to 11, we have an absolute min. We're now going to learn how to find critical numbers and then walk through some examples. Critical numbers are used to find where a function may have a maximum or a minimum value. Let's now see how a critical number is defined. A critical number of a function f of x is any number x is equal to c in the domain of f. That just means that our function at x is equal to c is defined, and then one of the following has to be true to have a critical number. Either f prime at c is equal to 0. That means that the slope of the tangent line to the curve is going to be equal to 0. Or f prime at c does not exist. When we have a function y is equal to x squared at 0, the slope of the tangent line is equal to 0, and that means that the derivative is equal to 0, and that means that at x is equal to 0, we have a critical number. Over here on the right, we have the function y is equal to the absolute value of x. When x is equal to 0, the derivative is undefined because we have a corner, and that means that the derivative doesn't exist, and that means that x is equal to 0 is a critical number. So a critical number just comes from where the derivative is 0 or where the derivative doesn't exist. Just to make things easier, I've written down a method that we can use to find critical numbers. The first thing you're going to do is calculate f prime of x. Then you're going to set f prime of x equal to 0 and solve for x, and that's your critical number. If f prime of x has a numerator and a denominator, this is where you just set the numerator equal to 0. And then the third step is you're going to find where the derivative is undefined. If f prime of x has a numerator and a denominator, this is where you set the denominator equal to 0 because that makes it undefined. Once you have that point, you have to then check if your original function is defined there. If it is, then that value x is a critical number. But if the original function isn't defined, where f prime isn't defined, then you don't have a critical number. We're going to walk through some examples so you can see exactly how this works. We're going to walk through some examples where we are going to find the critical number of a given function. I've written down a method that we can follow just to make things easier. The first function that we're going to find the critical numbers for is the function f of x is x cubed plus x squared minus x. Our first step is to calculate f prime at x. So let's do that. F prime at x is equal to 3x squared plus 2x minus 1. And then our second step is we're going to set that equal to 0. We can factor this. This is 3x minus 1 and x plus 1. That's equal to 0. And then if we set both of these factors equal to 0, we get that x is equal to 1/3, and we get that x is equal to minus 1. These two numbers then are our critical numbers. Over here on the right, I have graphed this function just so that you can see what it looks like when we have a critical number. When x is -1, the slope of our curve is equal to 0, and we have what's called a local max. And then when x is 1/3, we also have a slope of 0. And at that point, we have a local min. Let's now look at our second example. In this example, we're given that f of x is equal to x cubed plus x squared plus x. We're going to begin by taking the derivative. F prime at x is equal to 3x squared plus 2x plus 1. And we're going to set this equal to 0. Now we have to factor this. When I look at this, I cannot see an easy way to factor it. So we are going to have to use the quadratic formula. Let me just go ahead and put that over here. The quadratic formula tells us that x is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's see what this gives us. X is equal to negative b, so that's -2, plus or minus the square root of b squared, so that's 2 squared, so that's 4, minus 4 times a, which is 3, times c, which is 1, all divided by 2 times a, which is 3. Let's look at this part right here. That is equal to 4 minus 12, which is minus 8, and that is less than 0. So this tells us that we have no real roots. And whenever we have no real roots, we have no critical numbers. Let's now look at the graph of this function so that we can see what a function looks like when you don't have any critical numbers. Notice that our function is always increasing. The slope of the function is never equal to 0, and there are no max or mins, so there are no critical numbers. Let's look at our third example. Our function f of x is equal to the square root of x times 1 minus x. We're going to begin by taking the derivative. F prime of x is equal to, now we have to realize that we have to use the product rule. We have a first function and a second function. So our derivative is the first function, which is the square root of x, times the derivative of the second function, which is -1, plus the second function, 1 minus x, times the derivative of the first function. The derivative of the square root of x is 1 over 2 root x. If you haven't memorized that, that's probably worthwhile memorizing. It just saves time. Now we need to simplify this. Let's get a common denominator of 2 root x. So we're going to multiply this term by 2 root x. So that gives us a minus 2 root x times root x is x. So we have minus 2x. And then from the other piece, we have a 1 minus x. This gives us 1 minus 3x in the numerator. And then in the denominator, we have 2 root x. We are first going to check where the derivative is equal to 0. So we're going to take the numerator and set it equal to 0. So we have 1 minus 3x is equal to 0. And this gives us x is equal to 1/3. So that is a critical value. Now we're going to see where our derivative is undefined. That is going to happen when our denominator is equal to 0. So we have 2 root x equal to 0. And that happens where x is equal to 0. Now, we can't just assume that this is going to be a critical number. We have to go back up to our original function, and we need to see if it's defined at 0. F at 0 is the square root of 0 times 1 minus 0, which is just 0, and it is defined. So we can then know that x is equal to 0 is also a critical number. I've graphed our function up here on the right. At 0, we have what's called a vertical tangent, and that's why the derivative is not defined at that point. And then at our second critical number, the slope of the tangent line is equal to 0, and we have a local and absolute maximum. Let's now look at our fourth example. For this example, f of x is x to the 1/3 minus x to the minus 2/3. Let's take the derivative. F prime at x is 1/3 x to the minus 2/3. We just subtract 1 from 1/3. And then we have a minus 2/3 times x to the minus 2/3 minus 1. So that's a minus 5/3. Now let's go ahead and let's simplify this. I'm going to write our negative exponents in the denominator. So our first function is 1 over 3x to the 2/3. And then we have a plus 2 all divided by 3x to the 5/3. That just helps us to get a common denominator without having to deal with negative fractions. We can then see that our common denominator should be 3x to the 5/3. I'm going to make a note here that x to the 5/3 is x to the 1 times x to the 2/3. So we know when we get a common denominator that we're going to have to multiply this number by x because it already has an x to the 2/3. So this gives us an x plus 2. Now to find the critical number, we're going to take our derivative and we're going to set it equal to 0. So we're going to take the numerator and set it equal to 0. So we have x plus 2 is equal to 0. And this gives us x is equal to minus 2. So x is equal to minus 2 is a critical number. Now we're going to see where our derivative, f prime of x, is undefined. That is going to happen where our denominator is equal to 0. So we're going to set 3x to the 5/3 equal to 0. And that gives us x is equal to 0. Now, here's where the most common mistake can happen. We cannot assume that x is equal to 0 is a critical number without going back to our original function right up here and checking if it is defined at x is equal to 0. So we can check f of 0. This is 0 to the 1/3 minus 0 to the minus 2/3. This term is just 1 over 0 to the 2/3, and that is undefined. So that means that x is equal to 0 is not a critical number. Now let's look at our graph. When x is 2, it's a little hard to see because it's so small. We have a horizontal tangent, and the slope of our function is 0, and there is actually a local max at that point. And then you can see from our function that at x is equal to 0, our function is undefined and we don't have a critical number. Our last example is f of theta is equal to 4 theta minus tangent theta. I had to include one of these examples because when I've taught this in class, I found that the trig examples are the most challenging for students. We're going to start by taking the derivative. So we have f prime of theta is equal to the derivative of 4 theta, which is just 4. And then we subtract the derivative of tangent, and that derivative is secant squared theta. Now, I don't know about you, but I don't really have the secant values memorized. So let's see if we can change this derivative to be in terms of cosine instead of secant. So let's set secant squared to be 1 all over cosine squared theta. Now we can go ahead and get a common denominator, cosine squared theta. Now we're going to have to multiply our 4 by cosine squared theta, and then we subtract 1. Now we can find where our derivative is equal to 0. We're going to take the numerator, set it equal to 0. So we have 4 cosine squared theta minus 1 is equal to 0. This gives us cosine squared theta is equal to 1/4. So cosine theta is equal to plus or minus 1/2. Now we have to find where cosine theta is going to be plus or minus 1/2. Since it's a plus or minus, this value is going to happen in all 4 quadrants. So we're going to have theta is equal to pi over 3, because cosine pi over 3 is 1/2. And now to account for all the other values that are not between 0 and 2 pi, we have to say plus 2n pi, where n is equal to 0, plus or minus 1, etc. And then we have theta is, in the second quadrant, 2 pi over 3, plus 2n pi. In our third quadrant, we have 4 pi over 3 plus 2n pi. And then I'm going to have to put it over here. In our fourth quadrant, we are going to have 5 pi over 3 plus 2n pi. I have a lot of videos on trigonometry if you need to review any of that. Let's go ahead now and highlight our critical numbers. It's this one, this one, this one, and this one. Now we have to think about where f prime of theta is undefined. If we look back up at our derivative, f prime is going to be undefined where the denominator is equal to 0. But before we go ahead and compute all those points, let's go back up and let's look at our original function. Tangent theta is sine theta divided by cosine theta. So at points where our derivative is undefined, our function is also going to be undefined because it also has a cosine theta in the denominator. Because of this, we are not going to have any critical points from where the derivative is undefined. So these critical points that I highlighted in green are our only critical points. I went ahead and graphed this, even though the graph is really kind of hard to look at. It has all these lines because of the values that are to the right and the left, but what I want us to focus on is these points right here. These points that I'm going to highlight, those are our critical points, and you can see that they are local max and mins. And as we continue to go to the right and to the left, there are going to be an infinite number of those critical points and an infinite number of local max and mins. Let's now learn how to find maximum and minimum values of a function on a closed interval and then walk through some examples. The method used to find absolute maximum and minimum values of a continuous function that we'll call f on a closed interval from a to b is called the closed interval method. I have outlined what this method is. It has 4 steps that we need to follow. We first need to find the critical numbers, and then we need to check if each critical number is in the interval. Some will be, some won't be. Then we have to compute our function f at the critical numbers and also at the endpoints. And then our last step is we just have to compare these values that we found in step 3. Our largest value is our absolute max, and then our smallest value is our absolute min. I want to highlight one of the mistakes I see students make the most when they're doing the closed interval method. And that is in step 3, it's so easy to substitute the critical numbers and the endpoints into f prime, but you don't want to do that. You want to make sure that you plug them in to f. Let's now walk through some examples. We are going to find absolute maximum and minimum values of our function on the given interval. Our first example is the function f of x is equal to x cubed minus 6x squared plus 9x plus 2, and then the closed interval that we're given is from -1 to 2. The first step in our closed interval method is to find the critical numbers. So we're going to start by taking the derivative. Our derivative is going to be 3x squared minus 12x plus 9, and we are going to set that equal to 0. We're going to need to factor this, but notice that there's a 3 common to each term, so let's go ahead and let's pull that out. So this is x squared minus 4x plus 3 is equal to 0, and we can factor this as, let's see, we can have an x minus 1 and then an x minus 3. We set x minus 1 equal to 0, and we get x is equal to 1, and then we set x minus 3 equal to 0, and we get x is equal to 3. X is equal to 1, and x is equal to 3 is a critical number. Our second step is to check if each of these critical numbers is in the interval from -1 to 2. X is equal to 1 is in the interval from -1 to 2, but x is equal to 3 is not in our interval from -1 to 2. Let's highlight this number because that is a number where we're going to potentially have a max or a min. Let's go to step 3. Step 3 says that we have to find the value of f at the critical number in the interval and at the endpoints. So we are going to find f at 1. You just go back up to the original function. Let me go ahead and highlight this in yellow. And we're going to substitute in that x is equal to 1. Notice that we are not substituting it in to that function. Up at the yellow, we have 1 cubed, so that's just 1 minus 6 plus 9 plus 2. Let's see, if we add up the positive terms, we have a 12. So this is 12 minus 6 and we get a value of 6. Let's highlight that because that's one of the numbers we're going to have to compare. Now we need to find our function at each endpoint. So let's compute f at -1. Looking back up to the yellow highlight, we have -1 cubed, so that's -1. And then we have -6, -9, plus 2. Let's see, we have a -10, -6, so that's -16 plus 2 gives us -14. That's a number that we have to compare. And now we have one more. Our other endpoint, which is at 2. So f at 2 is 2 cubed, which is 8, -6 times 2 squared, which is 4, plus 2 times 9, which is 18, plus 2. So let's see, this is 28 minus 24, so that is 4. Now our fourth step is to look at the 3 values that we got in step 3 and find the largest one and the smallest one. The largest value is 6, so we are going to say that we have an absolute max equal to 6 at the point x is equal to 1. And now let's look at our pink values and see the smallest one. The smallest one is -14, so we have an absolute min equal to -14 at x is equal to -1. And those are our answers to our problem. Before we move on, I want to show you what the graph of this function looks like. It's graphed over here on the right. Notice that when x is equal to -1, that's our left-hand endpoint, we have an absolute min. And then when x is equal to 1, that was one of our critical numbers, we have an absolute max. And you can see that the derivative is equal to 0 because we have a horizontal tangent. Let's now look at our second example. This one has trig in it, and I always think the trig ones are the hardest ones, so I wanted to make sure and include this. Our function, f of x, is x minus 2 cosine x, and then our interval is from 0 to 2 pi. Our first step is to find the critical numbers, so we're going to start by taking the derivative. F prime at x is 1 minus 2, and then the derivative of cosine is minus sine x. Let's rewrite this as 1 plus 2 sine x. And now to find the critical number, we're going to set that equal to 0. So this is 2 sine x is equal to -1. And this gives us sine x is -1/2. I went ahead over here on the right and drew a unit circle so that we can find the values of x where sine is equal to -1/2. Sine of x is going to be negative in this quadrant and in this quadrant. Sine you always associate with y, and this is our y. This guy is our x. So when y is -1/2, so that's like right here, so that's this point and this point. The point on the right is going to be x is equal to 2 pi minus pi over 6. You can always think about reference angles, and you know that sine of pi over 6 is equal to 1/2. And this gives us that x is equal to, let's see, 12 pi over 6 minus pi over 6. So this is just 11 pi over 6. And then over here in our third quadrant, x is equal to pi plus pi over 6. I have a video on reference angles if you need to brush up on that. And this gives us x is 7 pi over 6. Our second step is to check if these two values, this one and this one, are within our interval from 0 to 2 pi, well, we picked them so that they were, so we actually don't have to do anything for this step. So let's just put that this step is done. So our critical numbers are 7 pi over 6 and 11 pi over 6. Our third step is to compute our function at the critical numbers and the endpoints. So we have 4 points to compute. Let's do the critical numbers first. F at 7 pi over 6 is 7 pi over 6 minus 2 cosine of 7 pi over 6. This is 7 pi over 6 minus 2, and then the cosine of 7 pi over 6, let's see, cosine is negative in the third quadrant, so we're going to have a minus root 3 over 2. So this is 7 pi over 6 plus root 3. And whenever you're doing a problem like this, we need to actually find the number because we have to figure out which are the largest numbers and the smallest numbers. So put this in your calculator and you end up with a value of 5.397. Let's highlight that in pink because that's one of the numbers we're going to have to check. Now let's do our other critical number. Let's find f at 11 pi over 6. So this is 11 pi over 6 minus 2 cosine 11 pi over 6. So this is 11 pi over 6. Hang with me. I know this is hard, but we can do this. Minus 2. Now let's think. 11 pi over 6 is in the fourth quadrant. Cosine is positive in the fourth quadrant. So this is a root 3 over 2. And this gives us 11 pi over 6 minus root 3. And this is approximately 4.028. And let's go ahead and highlight that. Now we're going to check the endpoints. These are actually easier. We have f at 0. So this is going to be 0 minus 2 cosine of 0. Cosine of 0 is 1. So this is just minus 2. That was a lot easier. Now we just have one more. F at 2 pi is going to be 2 pi minus 2 cosine 2 pi. So this is 2 pi minus 2. Put this in your calculator and you get a value of 4.283. And we'll highlight that. Now, we're almost done. Our fourth step is to look at all 4 of the values that we highlighted in pink and see which is the largest and the smallest. The largest is this one right here. So we can say that our absolute max is approximately 5.397 at 7 pi over 6. And then let's see our smallest value. Our smallest value is the only one that's negative, and that is negative 2. So our absolute min is equal to negative 2 at x is equal to 0. And those are our answers. Now, before we get done, I just wanted you to see the graph of this function. When x is equal to 0, we have an absolute min. And then when x is 7 pi over 6, we have an absolute max. And that's it. You've learned how to identify local and absolute maximum and minimum values, find critical numbers, and apply the closed interval method to find absolute maximum and minimum values. To really master these concepts, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.